All right, I'm going to make my presentation about gravity. Okay, and I'm going to start this with really a little history. Okay, and so let's go back a few thousand years and let's go to what they first thought the universe would look like. This is going to lead into gravity. Okay, so I'm going to share the screen and I want to show you this. Okay. A little bit of history of astronomy. Now, the first guy to really think about this and write stuff down was a guy by the name of Ptolemy. Okay. And he was actually a Greek, but the Romans hired him to be the governor of Egypt because at that time, Egypt was under the control of Rome. So the Romans hired this Ptolemy guy to be their governor. He was actually a Greek. And Ptolemy was actually a whole family of people. I believe his first name was Claudius, but there are a whole series of Ptolemies. Cleopatra was a Ptolemy, okay? And towards the end, when she got caught up with Mark Antony, killed herself with a snake, all that kind of stuff. It's a cool story. You should read it. But anyway, he was interested in the heavens, and he ended up writing one of the first books about astronomy, and that's what it was called. And in it, he advocated a geocentric universe. Geocentric, meaning geo meaning Earth, centric. So Earth was at the center of the universe. All right. And this was this at the time. If you look at his years, this was at the kind of like when Christianity began. So the church latched onto this, and they said, "Hey, that sounds like a good thing." So the church ended up advocating this theory as well because it fit in with their worldview. All right. Okay, and then and on it, he said the sun and the Earth was at the center, and the sun, planets, and stars moved on these fixed spheres that he called epicycles. Okay, and it kind of got a little complicated, but yeah. And this was the accepted theory for over 1,000 years until this guy came along, Copernicus. Now, Copernicus was Polish. He was a mathematician and astronomer, and he was interested. He didn't. He was a Renaissance man, right? And he did a whole rethink on this Earth at the center of the universe thing, and he used geometry, and he wrote a book. And in there's a lot of geometry in this book. I've seen this, and he tried to prove that the sun was at the center of the universe, not the Earth. And so he advocated a heliocentric universe, sun-centered. Okay. Now he spent his entire life working on this book, and he in his mind he never finished it because he was a perfectionist, so he wanted to perfect it. And so this book was not really published until he lay dying on his deathbed. His friends took the manuscript, got it published, and spread it around. And the story goes that as he lay dying, his friends laid one of the first copies on his chest, and he smiled, and then he died. That's the story. But the book wasn't really spread around until after he died. Now because he never really thought it was done, right? He was concerned that it kind of went against the teachings of the church, however. So he did float it to the Pope at the time, who I believe his name was Leo. He said, "Hey, Pope Leo, you okay with this?" And he came back and said, "Yeah, I'm okay with it." In fact, he wrote a foreword to the book. The Pope did. All right. So it wasn't because of church issues. It's just because he didn't really ever think that it was done. So now, but that revolutionized the view of the universe from Earth-centered to sun-centered. Okay. All right. Next guy to come along was Galileo Galilei, the Italian. Okay. And he, among other things, he invented the Galilean telescope, which was a big improvement on the crude telescopes that they had at the time. He didn't invent the two-lens optical device, but he perfected it and aimed it at the heavens. And with it, he discovered that Jupiter has moons. He also discovered that Venus has phases, like our moon. There can be a crescent Venus, there can be a first quarter Venus, there can be a full Venus. Okay. And if you have a really good pair of binoculars or a small telescope, you can tell this yourself. Okay. You can see that Venus has phases. All right. And these things implied a sun-centered universe as well, because if Jupiter has stuff that can orbit around it, why can't the sun have stuff that can orbit around it, right? And the only way Venus is going to have phases is if Venus is between the Earth and the sun. All right, so yeah, right. And he wrote a book too called this. But now the church had changed popes a few times, and now the church wasn't so into this. And so they actually brought Galileo to trial for heresy. They convicted him of heresy, and they sentenced him to house arrest. He couldn't leave his house for the rest of his life because of this, because it went against the teachings of the church. Don't worry, they've come around since then. Okay, the next guy in our story was a guy by the name of Tycho Brahe, and he was Danish, okay? And he was interested in astronomy and in alchemy. He was a rich guy. He was an aristocrat. Can you tell? The way he's dressed? All right. And he funded a laboratory, and he brought a bunch of people in to try to learn some stuff. And over the course of many years, for one thing, they plotted the position of the sun. They plotted the position of Mars over like 25 years. Okay, and they wrote it down in a little book, right? They also did some other stuff. They observed a nova, what later came to be called a supernova, all right? And he advocated this a geoheliocentric view of the universe, which I don't quite get. I've never really studied a whole lot, so I don't know what he meant by that, but that's what he advocated. Okay, the next guy to come along in our story, and somebody who actually went to work for Brahe, was a German by the name of Johannes Kepler, all right? And Brahe hired him, and Brahe said, hey, Johannes, take this Mars data. We've been writing down this Mars data for years. Can you make any sense out of it, you know? And Johannes said, yeah, okay, I'll try. And he used it to try to prove definitively that Mars was in a circular orbit around the sun. He tried to fit the data to a circular orbit of Mars around the sun, and he failed. Okay, didn't work. And he tried for years to make it fit a circular orbit, and just didn't work. So finally he gave up, and he said, instead of trying a circle, I'm going to try an ellipse. I want to see if Mars is in an elliptical or oval orbit around the sun. And using the data that Brahe's team had found, Kepler found that it fit perfectly. Okay, so he proved that Mars is in an elliptical orbit around the sun. And that was the first of his 3 laws of planetary motion, which I'm not going to really get into, but if you want, you can explore this a little further yourself. That link up there takes you to a simulation page. His 3 laws of planetary motion. And in particular, the third one found a mathematical relationship between the orbital radius and the orbital period of planets, okay? Okay, my point of all this is that this knowledge was built up over time, you know? People learned a little bit as they went, a little bit each time, all right? The next person in our story is Isaac Newton, okay? Now, before I get into his work on gravitation, I want to speak about something else. So I'm going to stop sharing for a minute, all right? And I want to do a demonstration in the back. So here, my monitor computer, here I have a stopper, and it's tied to a string. Okay? And I'm going to swing this around my head like this. So the stopper is in circular motion around my hand. Okay? Now, in order to keep the stopper moving in a circular motion, I must continually hold on to the string. If at any time the string broke or was cut or I let go, then the stopper would fly off on a tangent to the circle, literally tangentially to the circle, okay? But if I want to keep it in circular motion, I must continually apply a force on the stopper. And the force must be towards the center. I must continually tug on the string. I can't push it. I must continually tug on the string, no matter where it is in flight. I must continually tug on it to keep it in circular motion. This is a special force called centripetal force, or center, towards the center, okay? the center being my hand. All right. So centripetal forces, and they were known to Newton. And Newton also knew that the moon was in a circular orbit about the Earth, right? And he was wondering what was able to provide the centripetal force that kept the moon in a circular orbit. It wasn't a string. The Earth wasn't connected to the moon with a string. It had to be some other force. What was it? Okay. Well, also at the same time, the story goes that he was sitting under an apple tree and an apple fell off the tree and hit him on the head, right? Well, that's probably not really true. But he did observe an apple falling from a tree. And he asked himself, okay, what made the apple fall from the tree to the ground? And his answer was the same as your answer, gravity. But then he started thinking about this. Okay, let's say I take an apple and I climb the tallest mountain on Earth. And I hold the apple out and I release it. What's it going to do? It's going to fall to the ground. All right. Okay. Let's say now I get a ladder and I put it on the mountain and I climb up 2 rungs and I take another apple and I release it. Falls to the ground. Okay. Now I climb up 1 rung and I take another apple. He has an unlimited supply of apples. Okay. And release it from 1 rung higher. It's going to fall to the ground. Okay, then climb up another rung and do it again. Climb up another rung and do it again. Climb up another rung and do it again. He reasoned the apple would continue to fall to the ground. And in other words, let's say there was a ladder all the way to the location of the moon. When would gravity turn off from 1 rung to the next? Climb up 1 rung and all of a sudden there's no gravity anymore. That didn't make any sense to him. So he surmised that by this argument, gravity can act all the way to the location of the moon. And it was gravity that provided the force that kept the moon in orbit around the Earth. He was the first guy to come up with it. So he became very interested in gravity. Okay? And so he started to think a lot about it. And so he started to develop his universal law of gravitation, which I want to kind of go through the thinking steps of that. Okay. All right. So now he said, okay, so Earth attracts the moon. So gravity must be an attractive force between 2 bodies or any 2 masses, like these masses. Okay. And so there's an attractive force here. Okay. What affects the attractive force? What if he's thinking, what if I take and I double one of the masses? So I have a force of attraction here. Now, double the mass. What happens to the force of attraction? Well, he decided that it would double. Makes sense. Okay, now let's double the other mass. Okay, now the doubling was doubled again. Now it's 4 times. All right, instead of doubling one, let's, I don't know how I can arrange this, let's triple one. Okay, now the force from there to here is tripled. Okay, let's triple one and double the other. And then the tripling will be doubled. All right, so then it would be 6 times. Okay, so he came to the conclusion that the force is proportional to the product of the forces. I'm sorry, the product of the masses. Okay? Okay. Then he thought about distance. So I have a force between these two. What if I take and I double the distance? Okay? Well, he reasoned that the force would weaken. Okay? And but by how much? By doubling the distance, would it be cut in half? No? Well, no. Through the work of Kepler, he found, from Kepler, he got that if you double the distance, the force doesn't go down by 1/2, it goes down by 1/4. And if you triple the distance, it doesn't go down by 1/3, it goes down by 1/9. In other words, it's proportional to the square of the distance between them. And it's an inverse proportion. as the distance goes up, the force goes down. So it's inversely proportional to the square of the distance between them. Okay? Okay, now, writing this out mathematically. We get this. So force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Okay? Now, you can get from an equality to, from a proportion to an equality by multiplying by some proportionality constant, which had to be measured by experiment. So the next step in the process would be to get two masses, two known masses like this, put them a certain distance apart, measure the force between them. And from that, and if you want to do it really well, do it a number of times and make a graph out of it, make the graph be a straight line through manipulating it, take the slope of that line, and there's your proportionality constant. But Newton couldn't do it, you know? Newton died in 1727, okay? And he was unable, he didn't have the technology to measure this. Getting back to my presentation, the PowerPoint thing, okay? Newton, he put this in Principia, which is a lot of his work and his most famous work, okay? But he discovered and developed the law of universal gravitation, but he could not measure that proportionality constant. It took a guy by the name of Henry Cavendish in 1797, 70 years later, to come up with a way to measure that proportionality constant in an amazing experiment, one of the most amazing experiments in the history of physics. And so I'm not going to have you write this down. I'll give you the math. I'll give you the math version in a minute. But here's Cavendish's experiment. Okay, he had two massive balls on a rod that could move on a lab table, and then he hung two smaller ones from the ceiling with a flexible cord. Okay, and he set it up so that the ball was here, and the ball was here, and he let it come to equilibrium, and the balls that hung from the ceiling came to equilibrium. And he let it sit there a while to let it come to equilibrium. Then what he did was he moved this ball over here, this ball over here, a known distance away. Instead of he pivoted this rod. And then he left for the night. And over the course of the night, the smaller balls were gravitationally attracted to the massive ones on the other side now, and they pivoted a little bit, like on this dashed line. Now, the actual pivoting was much smaller than that, but it pivoted that way, and it twisted the fiber, okay? And that fiber had a mirror attached to it, and a light source that shined off the mirror onto a distant wall, and the movement of the light on the distant wall was amplified, okay? It amplified the twisting of the fiber. And Cavendish was able to work backwards. He knew what force would twist the wire. He measured all these distances, and he came up with the proportionality constant in a remarkable experiment. Okay? If the Nobel Prize had been invented then, he would have got it for sure. Okay? Yeah, very, very delicate experiment. Okay, stop sharing now. I'm gonna get out of there because I don't need it anymore. And stop sharing. And then, so Cavendish measured this proportionality constant. And Newton's law of gravitation took its final form of this. F is equal to cap G, okay? That's the constant, M1, M2 over R squared. Okay? Now, what do these things mean? What do these quantities mean? M1 is one mass. M2 is the other mass. r is the distance between them. R is the distance between them. And then G is this fundamental constant that has this value, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay, Newton meters squared per kilogram squared. All right, now this is called the universal gravitation constant, because as far as we know, it is constant throughout the universe. And gravity is one of the 4 fundamental forces in nature. The gravity, electromagnetism is another, the strong force that binds nuclei together, and the weak force, which is involved in a form of radioactivity. Those are the 4 fundamental forces in nature. That makes this number right here one of the most important numbers in physics. If this number were even 5% off, different than it is, then the universe could not exist as it does. If it was too small, then the matter could never come together to form stars and planets. If it were too large, it would come together too much. Okay, so this is an extremely important number in physics, one of the most important numbers in physics. Okay, all right. Okay, I want to use this in an example. And the example is going to come from the gravitation examples sheet that you can find in this week's Schoology folder. So pause this video and access the gravitation examples sheet, okay, in this week's Schoology folder. All right? Like this. Gravitation example problems. Okay, the first one, 2 balls have their centers 2 meters apart. One ball has a mass of 1 kilogram, while the other ball has a mass of 1.5 kilograms. Find the force of gravity between them. So example 1, I have, let's see, what do I have? The distance between them is 2 meters. One ball has a mass of 1 kilogram. The other ball has a mass of 1.5 kilograms. And yeah, and then we want the force of gravitation. And we have G, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. All right. So to find this, we're going to use Newton's law of gravitation. And so F is equal to G M1 M2 over R squared. So it's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times 1 kilogram times 1.5 kilograms all over 2 meters squared. All right, now this can be a challenge to enter into your computer or into your calculators, because there are a lot of calculators that if you enter 6.67 times button, 10 button, up caret button, minus 11, if you entered it like that, it's going to give you an incorrect answer. You need to look on a scientific calculator, you need to look for a button that's labeled EE or perhaps EXP. The vast majority of the calculators use one of those two. And that will be scientific notation. And I want to show you how to enter that on a calculator. Now, my go-to calculator is my $10 Target calculator, okay? And the EE button is located right above the 7. So when I enter this, I go turn it on first, 6.67, okay? E, and a little E shows up. Oops, actually exponential. And then negative 11. Now, your calculators might have a little button or a little thing down by the decimal point that's plus or minus. If it does, use that. If it doesn't, then your subtraction sign will probably work. minus 11. Okay, that's how you have to enter it there. If instead you have a graphing calculator, it won't turn on because I don't have batteries in it. The EE button is right near the 7, right above it. It's a second function that you access with the E. Okay. If you have one of these calculators, okay, then the EE button is located above the reciprocal one. See the EE above the 7, above the x to the minus 1 button? There's an EE there. That's how you enter this. So you enter that. If instead, now you can use any one of those calculators and it'll work for you. You could even use your phone, okay? But I don't really advocate using your phone, okay? And I'll tell you why. I'll show you how to enter this into your calculator, into your phone. You get something like this, okay? So access the calculator, get the more features by rotating it, and then you enter like 6.67, okay? And then the EE button is right next to the 1, E, right? E, and it should shade, indicating that's pushed. Negative 11. Do not use a subtraction sign. Oh dear, I messed it. I hit a button I shouldn't have. I got to start over. So 6.67. Oh dear. Come on. 6.67 E negative 11. Okay. Now the one thing I don't like about this is it doesn't show you if you're right or not. So hit equals, and it should say something like it should say that. If it did, then you entered it correctly. Okay. And then times 1. Now, how am I getting that? Well, let's look up here. Okay. So 6.67 E negative 11 times 1 times 1.5 divided by 2 squared. All right. Divided by 2 squared. And doing that on the phone, okay, times 1 equals times 1.5 equals divided by 2 squared. Now, there's no square button on this. Okay, there's no square button. So divided by, I got to go 2 times 2, and I got to enclose that in parentheses. Divided by, parenthesis, 2 times 2, parenthesis. And I don't even know if this is going to work. That actually worked, because that should be your answer. I don't really like using the phone because I don't know if I hit a wrong button or not. It doesn't give me a history, right? You can do it, but I don't advocate it, okay? There's even a way for you to do it on your computer, okay? You don't even need a target calculator. You don't need your phone. You can do it on your computer, and I'd like to show you how to do that. Get yourself a new tab, all right? And type in scientific calculator. Scientific calculator. Can you tell I've done this before today? And you should get this. Okay, now, so 6.67 EXP. Negative, subtraction sign in this case, negative 11. Okay? Times 1 times 1.5 divided by 2, and there's a squared button in here somewhere. Maybe there's not a squared button. Okay, so then I got to backtrack. I got to put the 2 in parentheses. Can I do that? Yeah, okay. Parentheses. 2 times 2. All right, parentheses. All right, so that's the 2 squared. And then if you equal sign, it'll give you this. And I like this because it at least gives you a history of what you did. So you can tell if you made an entry error. This is the correct answer. 2.5 times 10 to the negative 11. I'd like you to pause this now, and whatever device you're using to calculate it, get that number to come out. If you got it on your phone, you have a whole bunch of zeros. Oh, but now my phone, oh, that's kind of cool. Okay, let me show you this. I just discovered this now. I never use my phone as a calculator, so this is basically the first day I've done it. So you get there, okay, rotate it, And it'll give it to you in scientific notation. That's kind of cool. All right, that helps out. 2.5 times 10 to the negative 11. Okay? All right, and that's your answer. 2.5 times 10 to the negative 11. Units. Kilograms squared is canceled out by those 2 kilograms. Meters squared cancels out that, and you're just left with newtons. And there's your answer. Okay. Now, writing this out in a decimal form, you get that number that was on the phone. Okay. That number that had a whole bunch of zeros on it. Oops. You get that number there. Okay. That many newtons. Now, that is a darn small force. That is a tiny, tiny, tiny force. Okay. And that's why we don't see these two masses. Where are they? We don't see these two masses. Even if they're able to roll, the force of gravity is just way too small to overcome the force of friction. So you're never going to see them do that. Not on a table, but if they were out in deep, deep space, nothing else around, that very small force of attraction would cause them to start moving towards each other. As they got closer, the force would increase, so their acceleration would increase. And they would eventually stick together. And they would attract other things. And other things. And other things. And it eventually grow into stars, planets, so forth. Okay? This is what happened billions of years ago in the early universe. Okay? But on a scale like in this room, we don't see the effects of gravity until the masses are really big, because gravity is such an incredibly weak force. We don't really understand why gravity is such a weak force. Okay? There are a number of really exotic theories about why gravity is so different from the other fundamental forces. Okay, in terms of strength, it's really, really weak. Okay, but there's other strange things about it too that I'll get to perhaps another time, especially when we compare it to electricity, to the electric force. All right, but anyway, gravity is a very, very weak force until you get a whole lot of mass together, like the Earth, and then it becomes apparent. Okay. All right, I want to do another example, and that example is number 3 on the example sheet. So if you'll locate that example sheet, okay. I want to do number 3. And number 3 says, let's see here, the gravitational force between two spheres is 3.5 times 10 to the negative 7 newtons when they are 8 meters apart. One sphere has a mass of 5.00 times 10 to the second kilograms. That just means both zeros are significant. Calculate the mass of the other sphere. So, example number 3. The force between them is 3.5 times 10 to the negative 7 newtons. One of the masses is 500 kilograms. The other mass is unknown. That's the one we want to find. We know G, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And we also know the distance between them, 8 meters. Okay. What we want to find is M2. All right. So, Newton's law of gravitation, Gm1 m2 over r squared. Now, some of you at this point would insert the numbers and then solve for the unknown, and the unknown being m2. I'm not going to do that because I'm lazy. And instead of writing 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared all the time, which is how many things? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 things. Instead of writing 17 things, I want to write one, G, because I'm lazy. Okay? So instead of putting the numbers in, I'm going to solve for the unknown first. All right? And I can do that by getting rid of all the other stuff over here. For example, get rid of the r squared by multiplying by it. And when I multiply by it, it goes away on the right-hand side, and all I'm left with is G M1 M2. Over here, I got r squared F. All right, now I want to get M2 by itself, right? That means I got to get rid of the G, and I got to get rid of the M1. Divide by. Everything goes away over there, except for the M2. And what I get is, where should I put this? M2 is equal to r squared F over GM1. Okay? R squared F over GM1. Everything else cancels out. Now we put our numbers in. R, 8 meters. Don't forget to square that. Times 3.5 times 10 to the negative 7 newtons over G 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times M1, which is 500 kilograms. Okay. All right. Now, this is a complicated entry for a calculator to understand. You have to be very careful about how you enter this. Here's how most people would enter this. And instead of using this complicated example, I'm going to use, now note, 8 squared is like 64, right? Let's just count that as one number. So I have two numbers multiplied by each other over another two numbers that are multiplied by each other. Okay? Okay. I want to show you a very common mistake that students make when they're entering this into their calculators. To illustrate this, I'm going to use another example. 2 times 12 over 3 times 4. I got two numbers multiplied by each other over two numbers multiplied by each other. All right. Now, what should this be? Well, if I multiply across numerator, multiply the numerator, and I get 24. If I multiply the denominator, I get 12. Okay? 24 divided by 12 is 2. That's what we know the answer should be. Okay? Now, enter this into your calculator. Pause now, enter this into your calculator. What do you get? Okay. Did you get 32? That's wrong, right? Why is it wrong? Well, it's because you confused your calculator. If you enter it like this, and this is what a lot of people would do. 2 times 12 divided by 3 times 4. 2 times 12 divided by 3 times 4, right? Now, your calculator, multiplication and division have the same priority in terms of order of operations. So it would do it just left to right. And let's do this left to right. 2 times 12, 24. Divided by 3, 8. Times 4, 32. Okay, that's not what you wanted your calculator to do, but that's what it understood it to be. All right, now, to get around that, put the 3 and 4 in parentheses. Because now the calculator understands order of operations, parentheses first. So it will do this first, and you'll get 2 times 12 divided by 12. And 2 times 12 divided by 12 is 2. That'll get you the right answer. Okay, so if you entered it without the parentheses, You're confusing your calculator. Your calculator told you exactly what you, it wasn't the calculator that did something. You just put it in a language that you couldn't understand, right? Or it did something you didn't want it to do, all right? But it took what you entered and did it correctly, by the way. So you have to put parentheses around these, okay? Or there's another way around this. After any two operations, hit the equal sign on your calculator. And the other rule is, if it's on top, you multiply. If it's on the bottom, you divide. So 2 times 12 equals 24. Divided by 3 equals 8. Divided by 4 equals 2. Okay. Me, I do it the second way. If it's on top, I multiply. I just hit equals between anything. Okay. And then if it's on the top, I multiply. If it's on the bottom, I divide. Or put another set of parentheses around there. I want you to practice this. Your answer should be rounded 672 kilograms. Pause this now and operate this until you can get 672. All right, one more thing. Uh-oh. I keep breaking my meter stick. Oh, well. Not literally breaking, but knocking the magnets off of it. Then one more thing we can do with this is now we have a way to find, after Cavendish had his value for G, we finally had a way to measure the mass of Earth. Okay, because we know that the weight of something results from the gravitational attraction between that object and Earth. And I know what the gravitational force of attraction is for a 1 kilogram mass. It's the weight of 1 kilogram, or 9.8 newtons. So now, if I know the force, and I know one of the masses, okay, and I know the distance, and I know G, then I can find the other mass. And that's what we can do now. We can determine the mass of Earth, okay? Okay, bring us over here again. All right. Okay. Mass of Earth. That's my topic for now. So the weight, is this on screen? You see this? Zoom in just a little bit. Now, the weight of a 1 kilogram mass is 9.8 newtons. 9.8 newtons, okay? And this is the force of gravitational attraction between a 1 kilogram mass and Earth, okay? So remember from our previous example, if I know the force, I know one of the masses, I know the distance between them, and I know G, the other mass is the unknown. Oops, sorry. The other mass is the unknown. I'm doing the same thing, but this time the Earth is the unknown mass. Okay. So M1 is 1 kilogram. M2 is Earth. All right, we know G, 6.67 times 10 to the negative 11. Okay, and now, what about the distance? Well, this presented a problem, but by the time Cavendish came around, Newton had already figured it out. Okay, but it gave Newton trouble. So as if I have something sitting on the Earth, okay, and I want to measure the gravitational force of attraction between the two, what distance do we use? If it's sitting on the Earth, is the distance 0? Is that going to give me a proper measurement? Or can I take the distance from the center of the Earth? Is that valid? Or somewhere else? What's going to give me a right answer? And Newton struggled with this for a number of years. Okay, and he tried to prove it using the mathematics of the day. He assumed that you could, or he wanted to prove that you could. But the mathematics of the day did not allow him to do that. So what did he do? He invented the math. Okay, he invented calculus, and one of the reasons he invented calculus was to help him with this problem. Okay. Ultimately, he decided that you could take all of the mass of an object and concentrate it at the center, calling it the center of mass. All right, and you can take all your measurements from there. And so that essentially means that the distance that we need to take is the radius of the Earth, which was known at the time. The radius of Earth had been measured by a Greek a couple thousand years ago, actually. And so the R is equal to the radius of Earth, which was known, and in metric terms, its value is 6.37 times 10 to the 6 meters. Okay, that's the radius of the Earth. All right. So now we are in a position to calculate the mass of the Earth using the same expression as before. M2 is equal to R squared F over GM1. R, 6.37 times 10 to the 6 meters. Don't forget to square that. The force, 9.8 newtons. Over G, 6.67 times 10 to the negative 11. Newton meters squared per kilogram squared times M1, which was 1 kilogram. Okay. Pause this now. Operate your calculators. I'm going to give you the answer in a minute. Okay, the answer. 5.96 times 10 to the 24 kilograms. That's the mass of the Earth. Okay. Cavendish's measure of G made this possible. And by knowing the mass of the Earth, we could determine the mass of the moon using Kepler's stuff. And we could determine the mass of the sun. And we could determine the mass of all the other planets using Kepler and Cavendish's measure of G and Newton's law of gravitation. Turns out to be a big deal. All right. Okay. And that is a little bit about Newton's law of gravitation.